Please make sure you have your copy of today's assessment review in stoichiometry. Also make sure that you have a periodic table. Extra copies can be found up on the cart as always. You'll need a calculator and of course something to write with. So make sure that you are prepared and ready to begin for today's assessment review. As I go through the review, you can make sure to keep track of what we're doing by writing down the examples and then completing the problems that we don't do together. We'll look at these in our next class period. The things that you should be able to do: you should be able to balance a chemical reaction equation by choosing the correct coefficients to make the same number of atoms of each element in the reactants and products. In other words, that there's conservation of matter, conservation of mass. You should be able to calculate the molar mass of a compound using that periodic table. And you should also be able to use our stoichiometry solving steps to turn the mass of one substance into the mass of another. We'll review the X and the Y strategy that we've been following. If you're looking for more examples, of course, your textbook is always a useful resource. Use it like an encyclopedia of science. Our Moodle page with links to the assignments that we've been doing and also links to specific videos in our VHS YouTube channel. Go and check that out too. You can always get good stuff there. So, what will the assessment look like? There will be two unbalanced chemical reactions for you to balance. There will be a stoichiometry problem with some of the information given, and then there will be a stoichiometry problem where you'll have to figure out more on your own. Also, there will be an additional optional problem. This one you'll have to figure out and plan for yourself. The problem is to figure out how much leftover baking soda is in an Alka-Seltzer tablet. It's designed so that it has this many grams of baking soda. It reacts with citric acid in the tablet to make sodium citrate, water, and fizz. You can measure the amount of fizz that is produced in the reaction using a strategy that we've followed in our experiment, one of our experiments. And if you know how much fizz is made, you can calculate how much baking soda was used. And if you know how much baking soda was used, you can compare that to how much there actually was in the tablet, and then you can calculate how much extra there was, the excess amount. As you can see, there's not a whole lot else given to you. You'll have to do a lot of the work on your own if you choose to do that advanced level assessment problem when all the other assessment problems are completed. Let's start by balancing a chemical reaction equation. The first one. The strategy that we're using shows which are the reactants that you start with and the products that you end with, divided by the reaction arrow that points towards the products. Down the side, we'll list the elements that are in the compounds that are in the balanced reaction equation. And then in the space below, we'll count how many atoms there are of each element to start. And divide the problem into the reactants and products so that you can keep track of where you're trying to balance. Look at how many you have to start with. There are 2 atoms of oxygen in the reactants and 3 atoms of oxygen in the products, and those don't balance. So we need to put a number up at the top that's going to multiply and make the number of atoms equal. So if I multiply this by a 3, then this becomes 6. If I multiply this by 2, then this becomes 6. And now I have the same number of atoms of each element in the reactants and products, and this reaction is now balanced. That's what we're trying to do. Let's look at another example. Okay, good focus there. Now in this example we've got more substances. We'll begin by listing the elements down the side. We have hydrogen, boron, and oxygen. And I'll keep track of how many atoms of each element in each compound in the space below. There are 3 hydrogens, 1 boron, and 3 oxygens. And then over here in the products, 4 hydrogens, 6 borons, 11 oxygens. And over here, water, there's 2 hydrogens and 1 oxygen. So I'm looking to see if this is balanced. And I see, let me divide the reactants from the products here first. Keep track of which side is which. I see 3 hydrogens in the reactants and a total of 6 in the products. 1 boron, 6 on the other side, 3 and a total of 12, so clearly this isn't balanced. I'm going to look for something easy to fix, like this 6 and this 1. I can make this 1 into a 6 if I multiply the whole formula by 6. Multiplying this formula by 6 multiplies everything that I just counted by 6. So now there are 18 hydrogens, 6 borons, and 18 oxygens. Okay, let's see what I can do to make this balance. 18 hydrogens, and over here only 6. 18, and over here there are 12. If I want this side over here to be 18, if this 1 were a 7, then 7 plus 11 would make 18. Let's see what happens when I do that. If I multiply water by 7, then everything that I counted here gets multiplied by 7. And now I have 18 hydrogens in the reactants. I have a total here of 18 in the products. I have 6 borons in the reactants and 6 in the products. 18 oxygens in the reactants and a total of 18 in the products. Now this reaction is balanced. The coefficients on the top multiply everything that's in the formula. There's no number right here. There's an invisible 1. If I want to say that there's 1 of this compound, all I have to do is write its formula. It counts itself. But later on, when we do the stoichiometry solving strategy, you'll want to know what that number is when there's nothing in front of the substance. All right, let's look at the third one together. And we focus back a little bit. Start by listing the elements down the side. We have carbon and hydrogen, and then over here we have oxygen. And we'll begin by counting how many atoms of each element in each compound. 2 carbons, 2 hydrogens. Over here, oxygen, there's 2 oxygens. Divide the reactants from the products and keep counting. 1 carbon, 2 oxygens, 2 hydrogens, 1 oxygen. Okay, let's look for what's balanced and what's not balanced. 2 carbons, that doesn't balance. 2 hydrogens is already balanced. 2 oxygens, and over here a total of 3. Now, an even number and an odd total over here won't balance very easily. It's a lot easier to get things going if you first make this side even so that it can balance those oxygens. Let's try that by doubling the odd one. If I double this, let's see what happens. 4 and 2. Okay, now this 4 doesn't balance that 2. I can make this balance if I multiply this formula by 2. If I put a 2 here, that multiplies everything in the formula, so the 2 that I counted becomes 4. And let's see if I'm getting any closer here. Okay, this 4 doesn't balance that 1, so let me multiply this by 4 and see what happens. 4, now that's 8. Okay, now this 4 and that 4, they balance. This 4 and that 4, they balance. This is a total of 10, and it doesn't balance the 2. I could make that 2 into a 10 if I multiply this formula by 5, because 5 times 2 is 10. Alright, so now I've got 4 carbons on each side, 4 hydrogens on each side, 10 oxygens on each side. 2, 5, 4, and 2 would be the coefficients. The remaining problems you can try on your own, and the goal again is to find out what coefficients to put up that are going to multiply the formulas so that you have the same number of atoms in the reactants and in the products. Let's go through one of the stoichiometry problems. I'll do number 7 with you, and then you can work on number 8. The problem says that acrylonitrile, and here is its formula, is an important building block for synthetic fibers and plastics. You're probably wearing some right now. Over 2 billion pounds of this compound are produced in the United States annually. So that means that it's one of the most important chemicals in our economy. The compound is synthesized in the following balanced chemical reaction equation. Propene, which is a gas that's produced from petroleum, and ammonia, a naturally occurring substance, and oxygen gas, that's from the atmosphere. Those combine to make acrylonitrile, this material used for making plastics, and water. And the question says how much of this propene is needed to react with 2,450 grams of ammonia. So if I know how much of the reactants I have, that's what I'm trying to do. If I know how much of one reactant I have, I'm trying to figure out how much of the other I need to react with it. Now the strategy that we've been following uses X and Y to identify the parts of the problem. To identify the X, look for what you're given. Look at the number that's in the problem. You know where the question is because there's a question mark. So look for that when you're looking at a problem to know where the question is. And then in the question, look for the number. The number tells you what you're starting with. We're starting with this many grams of, and this is going to be my X substance, the one that I'm going to begin with in my problem solving. What am I trying to find out? I look for the keywords how much or how many, and that's linked to the substance I'm going to call Y. It's why I'm doing the problem, to try to find out how much of this there is needed in the reaction. The other thing I need to know are the molar masses of the substances. So I'll calculate for substance X and Y. For the X substance, I'll calculate the molar mass of ammonia. And for the other substance, my Y, I'll calculate the mass of the propene. Oops, 6. Okay, so to do that, I'll list the elements, nitrogen and hydrogen, and I'll count them. There's 1 nitrogen and there's 3 hydrogens. And when I look at the periodic table to find the mass of nitrogen, it's 14. We'll round to the nearest whole number. For hydrogen, it's 1. Now I'll multiply across. 1 times 14 is 14. 3 times 1 is 3. I'll add going down. 17. 1 mole of ammonia is 17 grams of ammonia. Let's do that for the propene. Formula for propene, carbon and hydrogen. Carbon is 3, and hydrogen is 6. Look at the periodic table for the mass of carbon. To the nearest whole number, it's 12. Hydrogen, the nearest whole number is 1. I'll multiply going across. 3 times 12 is 36. 6 times 1 is 6. I'll add those together. It's 42. So 1 mole of this formula for propene is equal to 42 grams of that formula for propene. All right, so now we're ready to begin setting up our equation. I'm going to start wherever I see X, I'm going to write the formula for ammonia. And wherever I see Y, I'm going to write the formula for propene. And then I'm going to look for the values that go in each place. The molar masses of those substances, and these question marks here we'll get to. Those come from the balanced reaction equation. So write down what you're given first. 2,450 grams of ammonia. And then I'm going to multiply by a fraction. On the top it says 1 mole of X, 1 mole of ammonia. And on the bottom it says the molar mass of X. I calculated that right here. 1 mole of ammonia equals 17 grams of ammonia. Then I'll multiply. And on the top it says moles of my Y substance, so I'm going to write moles of Y, C3H6. And on the bottom it says moles of my X substance, so I'll write moles of ammonia. Now the question marks in front, where do those come from? Those come from the balanced reaction equation. I have to look for how many moles of the Y substance, the propene, there are in the balanced reaction equation. So if this was my Y substance, and I look in front, I don't see a number there, that means that there's one of them in the balanced reaction equation. Now I'll look for my ammonia, and in front of that one I see a 2. This was my X substance, so I'll put 2 moles of ammonia for every 1 mole of propene. So when you get to this step right here, look at the balanced reaction equation for the coefficients. The last step says I'm looking for the molar mass of my Y substance over 1 mole of the Y substance. I know that 1 mole of that substance is this many grams. So on the top, 42 grams. And on the bottom, 1 mole. Now why are we doing it this way? We're setting up so that units cancel. All the units that I'm given, grams of ammonia, those will cancel out. Anything on the top and bottom of a fraction reduces to 1 and factors out. Moles of ammonia cancels out. Moles of propene cancels out. And the answer that I'm looking for, the question said how much of this is needed. Well, my unit that's left is going to be how much of that there is in grams. Now I'm ready to do the math. To do the math, multiply across the top. So I'll put that in my calculator. 2450 times 1 times 1 times 42. And I'll write down all those numbers. 102,900. And then I'm going to multiply across the bottom. Now when you multiply across the bottom, this number here, that does not multiply into the bottom. This is in the top. You could imagine, but you don't have to, that there's a 1 here, just to keep the place value. I'm going to multiply across 17 times 2 times 1. That's 17 times 2, which is 34. And then the last step, the top answer divided by the bottom answer. So I'm going to get 302. I'll just round it to that, grams of propene. Now in real life, the chemistry of this reaction is done on a much, much larger scale. 2 billion pounds of this are made every year. So we would need a whole lot more propene to make that happen. That's why we pump oil out of the ground, so we can make plastic. Alright, so there's another problem that's attached to this one. It says how much acrylonitrile could be produced from that same ammonia that we started with. And it gives you the molar mass of the acrylonitrile. Let's read the problem carefully. So I'm looking at the number. Here's the question mark, so I know where I am. I'm in this part. This is the question. And the number identifies this is my x. And I'm looking for what am I trying to find out. Here's the key words, how much. And so this means this is my y. So x and y are identified. So let me begin by setting up the problem with what I know. I know 2450 grams of ammonia, again. And I'm going to multiply by, and everywhere I see x, it's going to be ammonia. 1 mole ammonia. And I know the molar mass of that because we already calculated that here. 17 grams of ammonia. I'm going to multiply. And now I need to know how many moles of the Y substance. So in this problem, my Y substance is acrylonitrile. That's over here. So the number that's in front, I don't see a number here, so that means that there's one of those in the reaction. So let me put down 1. 1 mole, C3H3N. Everywhere I see Y, I'm going to write the formula for acrylonitrile. And on the bottom, how many moles of the X substance? The X substance was ammonia, and again that was a coefficient of 2 in the balanced equation, so 2 moles of ammonia. And then the last step, I need to know the molar mass of that acrylonitrile, and it's given to me right here. 1 mole of it equals 53 grams. So on the top I'll write 53 grams of that formula. And on the bottom, 1 mole of that formula. Now I'll let you finish off the problem by multiplying across the top. Take your top answer, multiply across the bottom, take your bottom answer, and then the top divided by the bottom equals the answer that you're looking for. And the unit is going to be grams of acrylonitrile because all the other units canceled out. The one that we were starting with canceled out, moles of ammonia canceled out, moles of acrylonitrile canceled out. The unit that's left is the one that goes in your answer. So there is another problem that you can work out yourself. Problem number 8. This one is about rockets, some of the first liquid fuel rockets made by a gentleman named Goddard. He used decaborane as a fuel, reacts spontaneously with oxygen from the air, and it's a very powerful reaction. You can do this problem, check it with each other. You can help each other out with that. And make sure to hold on to your work until next time so that we can finish our review before the assessment.